Yeah. You can also remove your mask if you want to. It will be better because otherwise they hear it as mumbling when they see us. They won't come in unless we have a crisis.
Okay, fine.
Hello everyone. Hope you are all been going through the NPTEL videos. The last 10 weeks are over now. The 10th week is going on. Adika?
Yes, the week 10 has been released recently.
So I still don't see many of them here, right? On the live session, in the YouTube. How many people are there in the chat? Anybody is there?
Nachiket is here saying hello.
Very good. So I see one student here. Omkar has written, please start. Feel free to ask questions now. Anyone else is here? How many people are online?
One is watching with him.
Watching?
Yeah.
Only one. Okay. Okay.
So let's start with Nachiket.
Yeah, you have any question, Nachiket? You can ask. Otherwise, we will look at the couple of questions which are put on the forum. One of the question is exponentiation of generators with iota. Why number of parameters of generators and number of generators are equal? Group elements of rotations, translations by writing generators in terms of observables. How to generalize it for arbitrary generator. Okay. So in the lecture, we can do that and transition it here. Okay. You went somewhere else. Go for that. Column. Will come in. Alt tab you did?
Yes, I did, but then it doesn't went to that white. Yeah, now it's white, but it's not showing the screen.
Do Alt tab again. Will it work? Yeah.
Okay. Now it is there.
Yeah. Okay, so first of all, you should know that when I say translation, okay, when I say translation, you can go along this direction, and also this direction. Okay. So translation along x direction by ax units, translation along y direction by ay units, and translation along z direction by az units is something which you can physically see, right? These are the three parameters in the sense that ax value can be, translation can be done from minus infinity to plus infinity if you don't put any bound, and similarly for ay and similarly for az. Okay. So these are the three parameters. So for every parameter, you should have some kind of a operator which helps you to take you from a position, let's say x to x plus ax. So there should be some operator which helps me to go from x to x plus ax. And that operator should also be possible on any function of x to x plus ax. Okay. So any function which is written at a position x, there is an operator which will help you to write the position x plus ax, and this is what I call it as a translation operator. And as you have rightly pointed it out, you can do a Taylor series expansion for this. Ax del by del x f of x, right, and so on. So you can do this Taylor series expansion. And if you take Ax to be small, if you take the translation vector to be very small, then the function is almost a function plus a correction. This correction is due to the generator of the translation. Okay, and you see that whenever I do that, the parameter will be there. Along with that, there will be a differential operator representation. To that file you can go. Does it work? I don't know. Oh, that's it. So you can go to the differential operator form, and as you have said that in quantum mechanics we know that IH cross d by dx is px. You can use this to say that the one which takes you away from f of x for an infinitesimal transformation is like the linear momentum operator. Okay, linear momentum operator. And linear momentum operator, you can press it again and it goes to a new slide maybe. So the linear momentum px, you can call it as a generator for infinitesimal translation. By infinitesimal I mean Ax is very very small, almost very very small. That's why you ignore all the higher order Ax square terms and so on. Okay, so clearly we know that this generator is like a Hermitian. Okay, Hermitian. What does Hermitian mean? That px is px dagger. Okay, and 1 minus I px times Ax by h cross on f of x. Right? This is for an infinitesimal one. I am taking Ax to be very small. So if you want, you can put a delta Ax to remember it is very small. And this is what will give you an f of x plus delta Ax. Okay. This procedure of translating it by delta Ax, again translating it by delta Ax, you can do it n number of times to get a finite transformation. Okay. So if you want to get f of x plus Ax, where Ax is going to be delta Ax times n, you can rewrite this as Ax by n and do it to the power of n. Right? You will do it so many number of times, and this by definition for n large you can show it to be an exponential operator. Is that clear? Are you all aware of it, Nachiket? Okay. So that's why you get an exponential operator for a finite transformation. You can write f of x with exponential of I px Ax by h cross will give you f of x plus Ax, where Ax is finite. So that's the way you can see an infinitesimal transformation as only two terms, and anything deviating from identity is what is called as a degenerator. And once you have the generator, then you do finite transformation as if you are doing it n number of times, that is why to the power of n, and delta Ax by this argument is Ax by n if you substitute and take the limit of, that's the definition of your exponential, right? Limit of n tending to infinity. Clear? So this is what gives you the exponential of a generator, and you normally get an I. One of the way to remember is that if px is Hermitian, okay, this operation, if you do the inverse of it, right, That's that. So you need exponential of px ax by h cross, then h cross. This product is identity. What is the meaning of this? This is translation in the positive direction by ax unit. This is translation in the negative direction by ax unit. So the product has to be identity, or equivalently you can see that it is a unitary operator. Okay. So this is a unitary operator. So whenever you demand a unitary operator as exponential of a Hermitian operator, you need to make sure that u dagger technically will be e to the plus I, px dagger, ax is anyway a real constant. If it is complex you have to put ax star, but it is a real translation parameter. So this is what you will have, but px dagger is px, which is the definition of a Hermitian operator. So you see that the exponential is important with an I factor so that u dagger u will be identity. Okay. Or equivalently, I can do this for this, another slide. I can do this for any arbitrary operator which is a unitary operator, I times h associated with the parameter a. Okay. If you demand u dagger u equal to identity, a is a parameter for any abstract transformation, this implies h should be h dagger. Okay. So this property on the generator that it is Hermitian will force that there should be an I factor in the exponentiation to find a finite transformation operator for any abstract transformation. Is that answering your question? So abstract transformation could be anything, any unitary operator by an exponential of IHA. But what you have to remember is for every generator it should be, the Taylor series has told you that generator multiplied by a parameter. Okay. So when you have 5 generators, and then you should have 5 parameters, like translation along x, y and z are 3 parameters. So you will have 3 generators, which is px, py, pz. Similar thing will happen in the abstract case also. If you have 8 parameters, you should have 8 generators, and then you have to take exponential of summation over all these generators with the corresponding parameters for an arbitrary transformation. Just like for an arbitrary translation, the unitary operator can be written as I p dot a by h cross, where it is px ax plus py ay pz az. For an arbitrary abstract group which I have written with 1 generator and 1 parameter, if there are 8 generators and 8 parameters, you will have I summation over some j, hj, the corresponding parameters aj, with suppose it is 8 parameters, you will have this to be the abstract group exponentiation, where these are Hermitian and then the I factor takes care of the unitary property for the unitary groups. Is that answering your question, Nachiket? He is answering something? Yeah, okay. I've also how to get this form after exponentiating the Lie bracket of 2 generators. So you don't need to exponentiate the Lie bracket of 2 generators. It is the Lie bracket comes out as a consequence whenever I do the operations of the unitary operators. Okay. So some simple example, I have probably explained it in the lecture. So in the rotation case, rotation about x-axis, rotation about y-axis. So let me say this is rotation about x-axis, and then if I do rotation about y-axis, you know it is not same as rotation about y-axis first and rotation about x-axis. You know this. Okay. So this can be written as exponential of minus I by h cross Lx times some theta x, and this one can be written as e to the minus I h cross Ly times theta y. Oops. Ly times theta y, and then what you can do is you can keep terms. I want to take the subtraction, okay, I take it to the other side, which is e to the ih cross Ly times theta y e to the minus ih cross Lx times theta x. Okay, so let's do this. Assuming theta and y are all small. Okay, so let's do the subtraction of these two operators, keeping theta x and theta y to be small. Okay, so what will happen? You will have a term which is identity, and then you will have a term with delta theta x with minus ih cross Lx. So do this exercise. Okay, this has been done in the lecture, but if you have not seen it, you should do it. And theta x with identity, and then you will also have a so you will see that this one will be Ly delta theta y, and then you will have a by ih cross Lx delta theta x plus I by h cross Ly delta theta y. So they will all cancel. These terms will cancel, and then you will have a delta theta x delta theta y, and that term will have a commutator of Lx with Ly. Okay. Fine. So this is what will happen when you are doing this. So it is 1 minus the commutator of this, and you can try to, because you will have an Lx Ly coming from here, Ly Lx coming from here with a delta theta y and a delta theta x. So this is a way you can pull out the combined one. If I try to write this combined one as some u operator with what it is, an infinitesimal one, as 1 minus delta theta z Lz. Suppose I do this, what you can show is that this piece will give you the ih cross Lz. So you can determine the V bracket of the generators by multiplying the group elements, which are exponentiation of the generators. I hope this answers your question. This has been discussed in the lecture, and you can go back and look at it. Okay. Yeah, regarding this, the coherence of density matrix of quantum systems, complete positive trace preserving maps, I am not taking it up here because this is confined to group theory applications, and those are in the context of entanglement issues, where we need to look at these density matrices, and quantum technology, quantum computers, where you need to worry about quantum decoherence. So these questions we will not take it up as a part of this live session. Anything involving the course we will discuss. The nuclear spin issue also, I think what you have to remember is that, just new page. So what you need to know is, for every state Lm, okay, so there is a associated tensor of, someone was also asked to explain the irreducible tensors operator. So let me explain it here. So L equal to 0, M is 0. This is equivalent to 0 and 0, which is sometimes called as a scalar operator. Okay. So this is a scalar operator. You can call this also as a tensor of rank 0. Okay. Tensor of rank 0. So this is both scalar operator sometimes is denoted as an irreducible tensor of rank 0, and there is a one-to-one onto correspondence between the states and the irreducible tensors where L's are all integers. Okay. So the next one will be L equal to 1, M equal to plus or minus 1 or 0. So this is 3-dimensional, right? The bases are 3 states are possible. Here it is 1-dimensional because there is only one unique state. Okay. So this is 3-dimensional. There is an equivalent representation which you can write it as T of 1 comma M. Examples are position operators. Okay, position operators, which I can denote it as x hat, y hat and z hat in your Cartesian coordinate, but you can also denote it as minus x plus iy or minus x minus iy and z. This is t0, t10. This one is t1 minus 1 and the other one is t1 plus 1. Okay. So these are equivalent ways of writing it using a linear combination of x plus iy and x minus yy, which has an interpretation as an irreducible tensor of rank 1, or sometimes we call that as a vector operator. So this is vector operator, which is an irreducible tensor of rank 1. This is irreducible tensor of rank n. The question asked is quadrupole moment tensor, where does it fit in? Okay. So this doesn't fit in. See, first of all, L has to be an integer, otherwise it's not a physical observable. L equal to 0 is a scalar operator. You can construct scalars using position operators, or momentum operators is also a vector operator. So you can have a dot product of position operators, dot product of momentum operators. They will all give you a scalar operator because it will be only one component, right? A dot product of two vectors A dot B will give you one scalar. You all know it. A vector operator will have 3 components, like dipole moment operator is a vector operator, and you will have 3 components. The quadrupole moment tensor is a higher rank tensor. Okay. So if you take L equal to 2, which is a rank 2 tensor, then you can call that to be the quadrupole moment tensor with L equal to 2 and M, which means how many components are there? M can take plus or minus 2, plus or minus 1 and 0. So there are 5 components. So this is what is the requirement for a quadrupole moment tensor. So obviously you see that the orbital angular momentum has to be greater than 1 for it to be a quadrupole moment tensor, and that's what probably one of them is asking when they say about the spin and quadrupole moment. And this also should explain to whoever has asked about a discussion on an irreducible tensor operators, that all these are irreducible. These are what we call it as a irreducible. What is irreducible about it? Tensor of rank L. Okay. So what is irreducible about it? It cannot be further broken down, and when you do some kind of a rotation, all these components will get mixed up. Okay. So when I do on a scalar a rotation, what will happen to a scalar under rotation? Nothing. The operation will be like an identity operation. Okay. In the lecture,
Text the same.
Yeah.
D. Ghosh has asked.
What?
Can you recommend a text or matrix representation?
That's right. So this was asked already here, right?
Yes.
Yeah. So let me come to it. Just before that, let me finish this. So this is what is the irreducible tensors. But you can construct taking such irreducible tensors, composing them. Okay. Can you go to the next page? So compose two of them. Okay, so let's take one vector operator M1 and then another vector operator. If you compose these two, then your expectation is that it can be rewritten in terms of irreducible tensors of higher rank. So 2 comma M1 plus M2, right? And then you will have T of 1 and then you will also have T of 0. Okay, so this way of writing it tells you that you can have all possible cases where M1 plus M2 should go from -2 to +2, this M should go from -1 to +1, this M should be 0. Okay, so you can compose irreducible tensors. When you compose it, you can further break it up into a linear combinations of again irreducible tensors. So that's the importance of an irreducible tensor. Someone has asked about matrix representation theories of groups. You take a look at this Hammermesh book and also my own book, and many books talks about it. I don't have any specific recommendation for any particular text or article. Even any quantum mechanics book do deal with a chapter like Schiff, right? A book by quantum mechanics by Schiff. He has a section on symmetries where he talks about matrix representations and so on. Any quantum mechanics book will also have a matrix representation theory of groups. So I don't have any specific book, but these books you can take a look at it.
Yeah. So Nachiket has also replied saying that how did exponentiate those generators with just an iota and no parameter, and said that you are good.
Okay, so many times many books don't write parameter times g, but technically when they write the g in the exponential of ig, it should be viewed as generator times some parameter formally. Parameter does not really play a role whether, only the generator you need to worry about whether it's a Hermitian or anti-Hermitian and so on. Parameters doesn't really play a role in this argument. So formally many books will write e to the ih and they don't put ih times the parameter. So for all practical purpose, independent of they mention the parameter or not, you have to know explicitly when you do some transformation that g has to be seen as parameter times the generator. Okay, so that's the way you should view it. Rajashekharan's book is very good for matrix representation. Maybe you can share it in the forum and you can share it so that others can also take a look at it. Okay. Any other question you have, or if you have missed anything? How to find the group symmetry of harmonic oscillator? Is it already gone to the transition, or you do see me here? Okay.
No, it's not there.
It's not showing the screen.
No.
Let's see.
It should be showing there.
Transition didn't work.
No. So it's transitioning between the screens.
Maybe you can call. It's not seeing us. How to find group symmetry of harmonic oscillator is the question, right? Okay. Thank you. Yeah. So now you should be able to see. Here it's not seen. Is it okay?
It takes some time to come here.
Okay. Fine. So group symmetry of harmonic oscillator. If you are doing 1D harmonic oscillator, then you know that V of x is equal to V of minus x. So the group symmetry will be just identity element and an element G where G squared is identity, right? It's a order 2 group. So that's the group symmetry of a 1D harmonic oscillator. If you're doing 2D isotropic oscillator, where you have V of xy to be half k x squared plus k y squared, where the spring constant is same for both x direction oscillation as well as y direction oscillation. Then the biggest symmetry is rotation about z axis. Rotation, all possible rotation by an angle theta z. Okay, so this collection you all know is going to give you and the determinant has to be 1 for rotations. It will be a special orthogonal group and you will take it to be, because you are doing it on a plane, it is only changing x and y coordinates to x prime and y prime coordinates. So it's an SO2 group. Okay. So this is the maximal symmetry of a 2D harmonic oscillator. 3D harmonic oscillator, isotropic, if you are taking half k, then you have x squared plus y squared plus z squared. You all know it is for an arbitrary rotation matrix and that should belong to SO3. So this is the maximal symmetry of a 1D oscillator, 2D oscillator and 3D oscillator. I hope this answers whoever has asked this question in the forum. Yeah. Why do we not include I times sigma basis for SU2 Lie algebra?
Means only poly basis you have?
Yeah. So the thing is, this also I have explained. Can you go to the next sheet? So when you do SU2, the lowest dimensional non-trivial dimension is 2-dimensional vector space. Okay. So you can put A and B. This should be interpreted as A times upspin plus B times downspin. Okay. Upspin state is 1, 0 and downspin state is 0, 1 in the matrix column vector notation. Okay. So this state, if I want to do a rotation, that rotation will be seen as an exponential of I times, I need to have a generator which is a 2 cross 2 matrix because the vector space is 2-dimensional, and that 2 cross 2 matrix should also be Hermitian, right? And what else is required? A parameter, corresponding parameter. Okay. If the rotation is about z axis, the corresponding parameter will be theta z and so on. Okay. So by H cross, operating on A and B. So this has to be a 2 by 2 matrix for the generators, and it should be Hermitian. Okay. And then if you do rotation about z axis followed by x axis, the algebra has to be satisfied. You need your algebra just like you had Lx, Ly. Oops. Next, can you go? Lx, Ly is IH cross Lz. You can do that with Lz sigma x, sigma y has to be IH cross sigma z. Okay. So exactly like the properties of your Lx, your sigma x should also satisfy, because in rotations the algebra, the Lie algebra of the generators are going to be, whether you are doing SO3 or SU2 Lie algebra, it is the same. So this is applicable for 2 cross 2 vector spaces, 2-dimensional vector spaces. This is applicable in your the physical angular momentum matrices, which are 3 cross 3 matrices in rotation in XYZ plane. So this algebra will force you that this has to be the polymatrices. Okay. If I am doing rotations about Z axis, then it has to be a polymatrix. Is that answering your question? I cannot be very clear about what you are asking, Nachiket, but why do we not include I sigma basis for SU2 Lie algebra? We do include it depending upon whether you are doing half odd integral spins or integral spins. Definitely for spin half you need the sigma basis. Sigma is the polymatrices basis. Is that okay? Anybody else is there? Any other question is there? But why did you again choose a subalgebra of SL2C for SU2? So, okay, so there are various ways in which you can see the SU2. Okay, so SL2C is set of special determinant has to be 1, linear matrices which are 2 cross 2 with entries being complex, and the number of bases there will be so many possibilities, and out of that you can have a subset which is a SU2 basis. So that is what is the broader picture of doing it from SLNC or SL2C to SU2. Is that okay? Otherwise we can just confine to looking at it as a rotation. The way we did SO3, we can do the SU2. Okay, but you can also do it from a broader picture of SL2C and look at what are the possible subalgebras. You know what is a subalgebra? It should be a closed algebra. SL2C has not 3 generators, or number of bases is not 3, it has 6, right? So out of the 6, 3 of them can form a subalgebra. This is what we are saying. No, the complete SL2C is slightly different from the SU2. SL2C does not put unitarity condition. It only says the determinant has to be 1 and it should be a linear operator. Okay, non-singular operators. But SU2 is, you need it to have determinant 1 and should also be unitary. That will reduce the number of independent parameters from 6 to 3. Please check it. Okay. So SL2C is not SU2. SU2 is sub-algebra of SL2C. Am I right? You don't have any unitary conditions in SL2C. Okay, looks like he is the only one who is attending. Don't see anybody else. Omkar is posting questions.
Five are watching.
Huh?
Five are watching.
5 are watching.
Still, we can wait for some more time to have questions.
Okay.
Yes.
Others are not asking questions. Okay. Anything else I left out which is pertinent to the syllabus? I think I've answered all the questions.
Yes, this is done. And
This also I said 2 of them are not going to talk about it. So exams are probably in the 3rd week of April or 4th week of April. So I hope you are all preparing well and do well in the exam. Of course, in the next 2-3 weeks, if you have any questions, you can post it in the forum and we will answer it. Okay, on the forum. If you have no further questions, you could leave in another 5 minutes or something, that you can let us know. We'll wait.
Nikita has made some other few questions also, but she didn't post it, saying that if we can discuss about why the number of, how to find the number of independent parameters in UN and SUN, and why there are different number of independent parameters for UN and SUN but same for ON and SON.
Very good. Let me explain that.
It's a good question.
Yeah,
actually.
yeah. So
Yes.
okay, you can
Transition.
transition. Okay, so SO3 is rotation or 3 cross 3 matrices with determinant +1. Okay. If you want to write O3, then you can have rotation times a matrix which is inversion. Okay. So this I will call it as an inversion matrix. What is inversion? Inversion, if it operates on x, y, z, the -1, -1, -1 will give you -x, -y, -z. So any vector which was like this will go into a diametrically opposite direction, right? This one will be a vector r from the origin, this one will be a -r vector. And that is created by the inversion. Okay, if you do inversion, then you see r vector becomes a -r vector. This is a discrete group. Okay, this one has the property that the group is identity and inversion. It's a discrete group of two elements. Okay. In the context of discrete group of two elements, you don't have this concept of generators. By generators, it should do an infinitesimal transformation, right? That's what I explained. An infinitesimal transformation in the context of inversion doesn't exist. You just take a vector and invert it. Okay? It's not an infinitesimal transformation that to get a finite transformation you do a series. It's not there like that. So there is no continuous group generator added for the O3 group. Okay. So if the SO3 group had set of generators, O3 will have the same set of generators because the inversion does not add a generator. Okay. So the number of generators for SO3 and O3 are same, SO and ON are same. But if you go to SUN and UN, okay, maybe you can change the slide. SUN, let's take SU2. You know the general matrices are E times I times, the generators are what we call it as J dot theta by H cross. These are the elements which I call it as U. Okay, U of theta. The collection of all possible thetas will give you the group, special unitary group, where it is determinant is 1 and the minimum dimension is 2 cross 2, and you can find what are the number of independent parameters in independent generators. We have done this. Okay, so this is 3. But if you want to write U2, what is U2? You have to take 2 cross 2 matrices. There is no determinant condition, but you require UU dagger has to be identity. This is all is required. So any SU2 element which I have written here, so maybe I can call it as some, yeah, so let's keep it as U tilde theta are SU2 elements. So if I want to write a U2 elements, I will write the element G as if it is U tilde of theta, and then I need to put a phase factor here. So G dagger is identity, right? If I put a phase factor, Unlike the inversion which you saw in the rotation, here it is exponential of I times some phase factor. Clear? So you can see that there is one parameter here added in the U2 when you go from SU2, because up to a phase factor. So this one is determinant 1, and determinant of G, which is U2 element, has to be a phase factor. So that tells you that the group element can be written as a phase factor multiplying the SU2 element. The phase factor gives you one more additional parameter, or equivalently you can say any UN is U1 times SUN. Okay. This has n squared minus 1 parameters. This has 1 parameter. So this one will have n squared parameters, which is not the case when you go from SON to ON, because this one will be replaced by a discrete inversion. Is that answering, Nachiket, your question?
No, it was just from the forum some other person.
Okay, someone has asked in the
Yes.
forum. Okay. What else?
Yes, I have from Nachiket this question.
All the symmetries which we observe physically are approximate symmetries. Some are exact. Some are, sometimes we take it to be, in some situations you can approximate those symmetries. Okay. Like for example, proton and neutron. You know what the mass of proton and neutron, right? Everybody knows, I'm sure, in the middle of this thing. There is a correction. Am I right? There is a correction. There is a delta M correction. Which is higher? Neutron mass is higher than the proton mass. Right? To see such corrections, which are exact, ma'am. No. So I'm saying there are symmetries which could also be exact. Like, for example, hydrogen atom problem. The rotation symmetry is the exact symmetry because it's spherically symmetric potential energy. So some cases where we see why proton and neutron have almost the same mass, why there is a correction, you can explain it by approximate symmetries which are like SU2 symmetries. And those SU2 has nothing to do with the spin, but there is some more new abstract cases we introduced called isospins. So in some certain situations you can treat it like an approximate symmetry, but in many situations it can also be exact symmetry. Okay? Anything else? Ma'am, in neutron and proton, do we take SU2 and not SO2? Yes, we do take it to be SU2. Because it's a unitary symmetry there, not the orthogonal symmetry. And that symmetry is isospin. If you are interested, you should take a look at the isospin symmetries. I do talk about it towards the end in the book when I talk about applications in particle physics. Okay. Okay, so good that we at least got to see the chat, but there are another 4-5 people watching is what you're saying.
Yes.
Okay. So do well in the exam. I hope most of you have got registered for the exam. Has to reach there. What reach there?
No, the continuous group still 2 more weeks are left.
Correct,
so
correct.
the isospin symmetry will be
Sure.
discussed later.
That's it.
Thank you for joining.
Thanks a lot for joining here, whoever is joined here online. And this probably will be our, we won't have any more live session, but you can of course put it on the forum, any questions, and we'll take it up. Okay? And wish you all the best for the exam. Bye.